So I'm discussing here two situations and we are trying to understand how these principal stresses will deform a particular body. In first situation, what I have said that I have a cylinder and that I am only applying stress from one direction, which is sigma v. And in the second situation, what I have said that there is sigma v from one direction and sigma capital H from all other directions, right? So, and you said you have only said that in the first situation it is easier to break this particular cylinder, right? And from there we have talked about something which we call as differential stress. Differential stress is the difference between the maximum stress and the minimum stress. So in the first instance, it is only sigma v because there is no other stress. So that is sigma v minus 0. So that becomes sigma v. And in the second situation, it is sigma v minus sigma capital H. Okay. So obviously, the differential stress at 1 is more than differential stress in 2, right? So hence, it is easier to break in first case. So what that shows that the absolute value of stress, okay, is not significant in determining deformation. Okay, so what do I mean by that? So suppose, in one case, in the same example, if I put, sigma v being 100 bar, and then from all other direction, sigma capital H being, also say around 95 bar. So the differential stress is 5 bar, right? Sigma v minus sigma capital H. In this is 5 bar. Now, if I have a second situation where, say, sigma v is 30 bar and sigma capital H from all other direction is, say, 10 bar. So differential stress sigma v minus sigma capital H is 30 minus 10, that is 20 bar. So you can see that although the absolute value of stresses in situation 1 is much greater than situation 2, but the differential stress in situation 1 is lower than the differential stress at situation 2, right? So if the differential stress is more, that means it is more favored for deformation. It doesn't really depend on the absolute value of stress. Okay. So that is where I wish to leave the discussion of stress. When you study structural geology, you will learn a bit more, a great more details about stress in the next semester. But for the time being, let us go for something called strain. And strain is the measurement of deformation. Okay. And in general, we are going to look at 3 types of strain. One we call as longitudinal strain. The second is called volumetric or bulk strain. And the third is called shear strain. All right. Now, suppose let us first look at longitudinal strain. And longitudinal strain is generally denoted with a word epsilon. Okay. Now, suppose I had a line of length L1. I apply some normal stress to it, and let us say the normal stress is extensional. Okay. Normal stress of sigma 1 to this particular body. Okay. And then after the application of the stress, this particular line actually extends. Okay. And the addition, after the application of stress, the length becomes L2. Okay. So epsilon or longitudinal strain is defined by L2 minus L1 by L1. Okay. Or in other words, delta L by L. Delta L by L1. Okay. Now, of course, if I put compressive stress, if I put compressive normal stress, what would happen? The length will decrease. Okay. So, the length will be L3. So, we can also write down, so in that case also I can calculate epsilon. Epsilon will be then L1 minus L3 by L1. Okay. So, what essentially means that I can put a modulus here, So I will only take the positive value. It's the difference between the final length and the initial length divided by the initial length. That is how we define longitudinal strain. Okay. So longitudinal strain can be extensional, positive. Yeah. In that particular case, the final length is longer than the initial length, and also it can be smaller than the initial length. Okay. In that case, the value of epsilon is negative. Okay. Now, this is how we define longitudinal strain. Okay. Now, if I vary sigma n, so sigma n means, deformation, that means I have to actually consider sigma 1 minus sigma 2, right? That means, the differential stress, the differential normal stress, and I vary that with epsilon. Okay. What I generally observe that the material, any material, for some time, actually for some amount of stress, behaves in a linear way. Okay. Behaves in a linear way. So what it means, and then after that, after some period in time, the material might simply break, or it can behave in a different way. It might not remain linear. Okay. It might not remain linear. So for the propagation of elastic wave, we are essentially interested in this limit up to this. When we study structural geology, we will study both, up to this limit and beyond. So we will study everything when we study structural geology. But for the time being, we are only interested up to this limit. Now, this is called the elastic domain. And then this is called the plastic domain. Okay. So what are the typical characteristics of elastic domain? The first one is sigma n is directly proportional to epsilon. Okay. So we can write down sigma n then is equals to y epsilon. Okay, then y becomes sigma n by epsilon. Do you know what is y? Y is a constant, of course. What is the name of y? Do you know?
Young's modulus.
Young's modulus. Young's modulus. And what is this law called? Where stress is directly proportional to strain. Here, normal stress, normal differential stress is directly proportional to longitudinal strain. What is this law called? Hooke's law. Okay. Now, so the first thing is sigma n is directly proportional to epsilon. Okay. The second important thing is that the strain is recoverable. Strain is 100% recoverable. What do I mean by that? Suppose, so I apply, say this is, 50 bar of stress. Okay. And suppose then the strain becomes something like 0.8, because it's a strain is a dimensionless quantity, right? Strain is a dimensionless quantity because it is delta L by L. So that means both of them have the unit of length. They cancel out. So it is a dimensionless quantity. 0.8 means, I can see that this is perhaps, so so around 80% strain, right? Now, if I remove this 50 bar to 0, if I now remove the 50 bar to 0, what I will observe in a perfectly elastic material, that the strain will become also 0. Okay, that the material will completely be unstrained. Okay, and this is the analogy is with a spring. Okay, so if I extend the spring, that means I'm providing some stress for which I can extend the spring. Right? So that means it is getting some strain, it is being strained. If I remove the stress, the spring goes back to its original position. Okay, and this is an analogy with an elastic material. That means the strain is 100% recoverable. Okay, and in case of elastic wave propagation, what we see that the collisions, suppose when I'm making a bang here, okay, I'm making a bang, that means I'm creating some elastic wave, and then the elastic wave is propagating from, so suppose I have a media. Okay, media means a lot of very closely spaced molecules and atoms. Okay, so when I am making a bang here, okay, I am creating an elastic collision. Elastic collision means a deformation in the elastic domain. A deformation in the elastic domain. Okay, so and then, so when I'm making a collision, I'm making a deformation in the elastic domain, and then that energy is kind of propagated through the media. And how it is being propagated? By doing small elastic deformation in the media. Okay, and the elastic deformation, slowly propagates from one place, from one side to the other. So what if I look closely, what essentially happens? It happens that suppose the grains are at a distance. What we observe that at one place the grain comes close to each other, and the other place the grains become away from each other. So it's like a pendulum like motion that starts to happen within the grains. Okay, and then again the grains can be close to each other and again away from each other. Okay, so such regions where, okay, the grains come together, they are denoted as C, okay, or compressional domain, okay, and then the areas where the grains move away from each other, okay, they are called R, or the relaxation domain. Okay, so in this particular case, what I am showing that an individual grain is actually propagating, in the direction of the wave propagation, in the direction of the wave propagation. Now, the elastic collision can also happen in a way where, I make a bang, okay, and what I observe that the grains actually start propagating in the perpendicular direction to the propagation of wave. Okay. So we will discuss this later on in bit more details. Such waves are called compressional waves, or P waves, and such waves are called shear waves, or S waves. But the fundamental is that it starts with an elastic deformation, and the elastic deformation essentially continues through the media when the wave actually propagates. Okay, because the elastic deformation is not permanent, as you remove the stress, that means when the wave completes its propagation, the media remains unstrained. The media doesn't change its shape or anything. Okay. So this is what we call as, this is the relationship between your normal stress and longitudinal strain. Now we have said there are two types of mode strain. The other one we call as volumetric strain, or bulk strain, and this is often designated with a word K or kappa. Okay. Same kappa, volumetric strain. Okay. And volumetric strain is, suppose I have a sphere of volume V1, okay, and then I apply some stress. Can you tell me what type of stress should I give on this material so that the volume, uniformly changes to V2? Okay, it can either increase or decrease. Okay, the volume uniformly changes from V1 to V2. Either it decreases, or it increases. So what sort of stress is that? What sort of stress can I put to make such changes? Can you tell me? We have discussed this. There is a very particular name for such stresses in nature. You understand that there is a sphere of volume V1, which is, upon the application of stress, it kind of shrinks, becomes V2, or it kind of expands and becomes V3. Okay, so what sort of stress should I provide to the system? Can you tell me? It is pressure, right? It is pressure, or P, because it is uniform from all sides. It's isotropic, right? So suppose V1 minus V2 is delta V. Okay, so then P will be directly proportional to delta V. Okay, similarly, so volumetric strain volumetric strain. Will be delta V by V1. Let us say that is K. Okay. So what we can say, P is directly proportional to K. And then I can essentially bring in another constant here. So P will be, suppose we provide kappa K. So here kappa is called bulk modulus. Okay. Here kappa is called bulk modulus. Right. Now, the third case we wish to discuss is called shear strain. Okay. So suppose I have a shear strain or angular strain. Okay. Suppose I have a like a square, okay, and then I apply some shear stress here. I apply some shear stress here, and the material is deformed, and it makes a shape like this. Okay, and the change in angle here is suppose theta. Okay, so shear strain will be equals to tan theta. Say shear strain we define as let us say S equals to tan theta. So we can say tau is directly proportional to S, and then tau can be equated with a constant. Sorry. And this is what we call as shear modulus. Okay. This is what we call as shear modulus. Okay. Now remember that like we have shown epsilon and sigma n, within the elastic limit they are linear. Similarly, within elastic limit, pressure and volumetric strain will also be linear, and within the elastic limit, shear stress and shear strain will also be linear. Okay, this is what happens within elastic limit. So once that linearity is lost, yeah, once that linearity is lost, that means we are away from the elastic domain, and it's no more elastic collision. It's no more elastic deformation. Okay, but for our purpose on the discussion of seismic, we will mostly concentrate ourselves within the elastic limit. Any question? Come on. Anything you did not understand? Okay. So if you have understood it, then I will just stop the class here today, because that is a natural stop. What we will do tomorrow, we will use this concept of we will use this bulk shear and um, bulk modulus, shear modulus, and Young's modulus to derive the typical equations applicable for PUA propagation and SOA propagation. Okay? That is what we are going to do in tomorrow's class. All right, then, shall I stop it here, or you have anything else you want to discuss about your quiz? Okay, if not, there is another thing. After uh, this on Friday, okay, what I will do, I will send you an assignment where also you have to read certain papers. So I will again divide you into groups and assign one scientific paper for each of you, okay, which is mostly around magnetics and gravity, which you have to read and then make a presentation like you did for the last time. All right, so that I will do on Friday, and you will have a week to actually submit your assignment. All right, then I stop it here and see you tomorrow. Thank you.